Competitive balance is an important topic in sports economics for two reasons. One, the uncertainty of outcome hypothesis, which is often abbreviated UOH for uncertainty of outcome hypothesis, obviously, states that fans care about uncertainty. We don't want to watch games where the outcome is known. We would like to be surprised by the outcome, or at least think that there's some probability that anything can happen. Either team can win, or tie if you're playing soccer or hockey. So this is why fans would care. There's also a reason to study competitive balance, and that is to see the effect of certain league policies on competitive balance, often referred to as the analysis of competitive balance, so ACB sometimes abbreviated. And this is using measures of competitive balance to see the effects of league policies on the distribution of talent. For example, if a league decides it's going to cap salaries so you can't spend above a certain threshold on your roster, we could use measures of competitive balance to see if such a policy distributed talent differently or prevented the same teams from winning the championship over and over, as is often given as a reason for why you would want to cap salary, perhaps, to keep things more interesting. But whether or not people care, whether or not they're willing to pay for it, whether or not it affects fans' welfare, that is testing whether or not the uncertainty of outcome hypothesis is true. So we could use competitive balance measures, use variation in how competitive leagues are across time or across leagues maybe, and see how that affects fans' attendance or willingness to pay for sports entertainment in any way. So we're going to derive a very simple measure of competitive balance that you can easily measure in data for your favorite league and use in your own research. So first, let's think about what a competitively balanced league looks like. And for the sake of argument here, I'm only going to consider leagues where the outcome is win or lose. There are ways to measure competitive balance with ties. It's a little more messy and a little more thought needs to go into it. And I can direct you to those papers or methods to do so, as I myself wrote a paper on how to measure competitive balance when there are ties, only to find out that someone else had published the same idea, I think, a year before. But in any case, we're going to proceed here as if we're only talking about MLB, NFL. Well, I guess NFL has ties, right? But we can just ignore those because they're so infrequent. But let's think about a league, whatever the case may be, that only has wins or losses, no ties. Well, we would think a perfectly competitive league, each team would have a probability of winning each game of 50%. So at the end of the season, we would expect each team to have approximately 0.500 winning percent. Or I guess that's a ratio because it's out of 1, but you get the point. So the win percent is 50%, or as is often displayed, 0.5. Well, now let's think about a simulated league, and this is very interesting because we can do this by hand. You can do this with a computer. Let's think about a simulated league where we program all the teams to be just as strong as one another, but the outcome is random. So since there's no ties, somebody has to win, and so there's some randomness to each game, and it's basically like flipping a coin to determine who wins. Let's start with an example of a very simple case, just to calculate. A 3-game season. So there's a season in some sport, whatever sport you want to imagine, and let's imagine there's only 3 games in the season, and ask the question, what are the possible outcomes for a team? So I'm basically asking here, what are all the different winning percentages that we could possibly see? Well, let's think about this. Get a new sheet. We'll start with game 1, and this is going to look like a game tree for those of you that are used to game theory. The only difference here is we're going to be looking at the paths a team could take, but it's not the team's choice. If it were the team's choice, they would always want to win. So game 1, we have 2 possible outcomes. The team could either win or lose, right? And then game 2, label the nodes out here. It's the same thing, right? You could either win or lose. So then there's 4 potential outcomes for 2 games. And then in the final game of the season, game 3, once again, you can win or lose. I'll go ahead and label these just to be clear. So going left is always winning, going right is always losing. And then at the end of all that, our team will be located at one of these final nodes, which will then assign to the team the winning percent depending on what happened. So notice here we have 8 different outcomes for any given team. And these outcomes are end of season outcomes. You'll be in one of these final nodes that will determine your winning percent. Now, what's the probability? Let's think about this. What's the probability in this league where you have a 50-50 shot of going left or right at any given node? Because it's an equally balanced league, we're assuming. If you have a 50% chance of winning or losing any given game, what's the probability that you get exactly 0 wins? Well, if we look here, there's only one way that could happen. You could lose your first game, lose your second game, and lose your third game. So the only way we could possibly end up in a situation where we have 0 wins is if we traveled this particular path right here. So there's only one node out of the 8 under which you would have a winning percentage of 0. That's the only way, because any other path, right, if we go this direction, we win. If we go left here, we win. If we go left here, we win. So we have to go right on each node and lose every game. So that is to say there is only one way out of all 8 outcomes. There's only one outcome that has us winning no games. So the probability is 1 out of 8, which is 12.5% if you want to think about percentages. So there's a 12.5% chance, or 1 out of every 8 times we simulate this league, that if all teams, and here there's only 2, well, I guess it doesn't matter how many there are, but from one team's perspective, if you have a 50% chance of winning any game and you play 3 games a season, then there is a 12.5% chance that you'll win no games. Or 1 out of every 8 seasons, approximately, we would expect you to lose all your games. So notice here we have to assume some kind of randomness, because you would think maybe equal teams only tie each other. Well, the only way you could win or lose is if there's some randomness. And that's easy to think about because you might think, for example, about games where there's a continuous clock, so not baseball, and you might think that if both teams are just as strong as each other, there is some constant rate, perhaps, of scoring points, but only one team can score at a time. And so it might just be random when the clock stops as to who scored last and won the game. Now, this was a calculation that we can easily eyeball here. However, there is some mathematics behind it. Let me go ahead and get rid of some of these reds. I'm going to have to rewrite my probability. That's fine. 1 out of 8. There's a mathematical way we can derive this probability without just eyeballing a diagram. As you can imagine, as the games get longer in the season, or there are more games, this will not be as easy to do. So the general way to get this probability of any given outcome, for example, the probability that we have no wins in this league, is a simple calculation, and the way we can read it is it's 3 choose 0 over 8. Now, I'm assuming most of you have had probability, and you're familiar with this from when you studied the binomial distribution. This is saying we'll have 3 sort of experiments, three different outcomes, right, of 3 games, and we're going to choose 0 successes. So we're basically saying how many ways can we have exactly 0 successes when there are 3 games? So 0 wins in 3 games. And this is basically modeled as saying, what if I flip a coin 3 times, and we'll call heads a win? What's the probability that I have no wins? Well, if you recall your probability mathematics, you might recall that 3 choose 0 is equal to whatever number's on the left, 3 factorial, over whatever number's on the right, 0 factorial, times the difference between the two. So 3 minus 0 factorial. Now 3 minus 0 is just 3, so we can ignore that in this case. 0 factorial is just the number 1, so we can basically ignore that. So in this case, what we actually have is just 3 factorial over 3 factorial, which is just 1. That's the same number. So what this says is there is only one way that you can have 3 games that are a coin toss and have exactly 0 wins. Now in general, the formula NCR, where N is the number of trials, that's how they usually describe it, and R is the number of successes. In general, this is N factorial over R factorial times N minus R factorial. So for any number, you can just plug in your N and your R, and this is how we calculate the number of different ways we can attain such an outcome where we have R victories, we'll say in this case. So let's do a couple more. What about the probability of winning exactly one game? Well, all I have to do here is change that 0 to a 1, 3 choose 1, and change it here, which means that 3 and that 3 become a 1. Let's go ahead and erase all that. That's going to change. So we have a 1 here. Oh, sorry, no. The 3 stay. What am I thinking? The 3 stay. The 0 is what changes. So we're going to have a 1 here and here. Now, 1 factorial is the same as 0 factorial. It's still 1. It's kind of an oddity, but it's a fact. So we get rid of that. The thing that changes is that this becomes a 2. So what we end up having in this example is 3 factorial over 2 factorial. I'll clear some space down here to show you what that is, because some of you, probably all of you, don't use factorials a whole lot in your life, even though you learned them, I'm guessing, in high school. 3 factorial over 2 factorial is the same thing as saying 3 times 2 times 1. That's what a factorial is. We multiply the number by each integer below it until we get to 1. Divided by 2 factorial, which is 2 times 1. Now, the convenient thing about having ratios of factorials is you can just cancel out all the like terms, and it makes it easy to solve here for the number 3. So the way we interpret that is there are 3 ways in which a team can win exactly one game when there are 3 games total. Okay, so again, 3 games total, 3 is this number. How many ways can we win exactly one game? That's this number. This 3 is the answer, meaning there are 3 different ways we can do that. Now let's look back at our graph, because here it's a very simple 3-game season, so we can check that. How can I win exactly one game? Well, I can win here and then lose the next 2. So that's one outcome. I can lose the first game, use green, lose the second game, and win the third game. Or, use blue circles now, I can follow that path, but win the second game and lose the third game. So let's keep track of these. This is another path that has me with 1 win. This is another path with 1 win. And that's it. That's our 3, right? 1, 2, 3. We have 3 different ways we can win exactly one game if there's a 3-game season, and it's a 50-50 shot. So then this is 3 over 8, because the probability of winning exactly one game is the 3 paths in which that happens divided by the 8 total paths we have. Lastly, it's possible to win. Nope, we could do 2 and 3. So let's keep going. We only have a couple left. What about winning exactly 2 games? So we'll change that to a 2. Let's go ahead and erase this. Actually, I'm just going to go ahead and clean this all up because we got a lot here. Okay. So we want to choose 2. How can we get 2 wins? So our formula will say that 3 choose 2 is, once again, 3 factorial divided by the number of wins, 2 factorial, divided by 3 minus 2 factorial, which is just 3 factorial divided by 2 factorial, because 3 minus 2 is 1, and 1 factorial is just 1. So we get the same answer here. So the probability of winning exactly 2 games is, once again, 3 out of 8. Let's check our simple diagram here and see if that's the case. Let me see if I can precisely erase these. Well, maybe not so well. Then redraw some of that. No problem. That's a win, that's a win, that's a loss. All right, so what are all the ways we can win exactly 2 games? I can win the first 2 and lose the last one. So there's one path. I can win the first one, lose the second, win the third. There's another path. I can win the first, lose the second. Oh, nope, that's another loss. I can't do that. Let's back up. So that's the only way I can get 2 there. I can lose the first, win the next 2. There's another path. So let's mark these 1, 2, 3. If I lose 2 games, then I can't win 2. So we're out of options. That's it. That's the 3 paths. Okay, what are the odds I win all 3? As you might imagine, this should be the same as the odds that I lose all 3. Well, we'll find out. So this is going to be 3, choose 3 over 8. So let's replace some numbers. These 2's will all become 3's. Actually, we don't know what that's going to become, so we'll erase that. So this is a 3 and this is a 3. Well, what we have is 3 minus 3 is 0 factorial, which is equal to 1. So yeah, we just have, once again, 3 factorial over 3 factorial, which is 1. So there's only one way to win all 3 games if there's a 3-game season. So the probability that that happens if you have a 50-50 shot of winning each game is 1 out of 8. And obviously that makes sense because there's only one path in which you win all games, and that's, well, the path in which you win all games. Okay, so what we're doing here is we're modeling what we call an ideal league. Now, who's to say it's ideal that everyone has a 50-50 shot of winning? That's subjective, obviously. But in the literature, this is what they refer to as an ideal league. And we compare the outcomes of actual leagues to this ideal. So one thing we like to do is look at a histogram of team outcomes for the season. And this is something you can actually do with data. So frequency is on our y-axis. That's the frequency, how often we see this. And we're just going to continue with our example with our team. And the question is, how often, we're actually going to put a 0 here, do we see 0 games won, 1 game won, 2 games won, and 3 games won over the seasons? And our probabilities or proportions or whatever we want to call them is 1/8 and 3/8. Oops, not 1/3, 3/8. That's what we were seeing. And so if we made a bar chart or a histogram of this, we would see that there's a 1/8 probability of losing all games and actually of winning all games, and a 3/8 probability of winning 1 or 2. Maybe I'll just shade this. So imagine these are filled in. I don't know that I have the ability to do that on this program, so I'm just going to kind of scribble in here. So this is our histogram. And if you want, we can think of this in terms of winning percentages. So this is 0, this is 0.333, 1 out of 3 games, 0.666 out of the beast, and this is us batting 1,000 in terms of winning games. So you can measure this in terms of wins, but more likely we measure this in terms of percentage of wins. That way it's comparable across seasons with different number of games. So it's actually more common for us to refer to these percentages rather than the number of games won. Now, this looks kind of familiar for those of you that took probability, which should be everybody. And if we were to do this exercise for seasons with more games, right? If there were 4 games, we would have to add a 4 here. If there are 5 games, we'd add a 5, right? As the number of games goes to infinity, this thing would spread out and start to look a lot more like a normally distributed variable. So we'll have that symmetric bell shape. This is what you get with a binomially distributed variable. As we increase the number of trials, which is here the number of games, the possible outcomes take on a normal distribution, or the average or the expectation will be somewhere in the middle. So another way to think about this is, if we were to look at, instead of a single team, if we were to look at the distribution of all teams, it would still look like this. So the percentage of all teams that won a third of their games would be 3/8. If I plotted the winning percentage of all teams, think about it, an actual league again, the percent I would expect to have that attained a winning percentage of about 66 or 67%, or 2/3 of their games, we would expect, again, 3/8 of those teams to have a winning percentage that high. Now, again, this is for the hypothetical league with 3 games. We would have to recalculate this for an actual league. So if you're looking at Major League Baseball, they have 162 games, right? We would have to redo this where the number of games is 162. So these percentages would be much lower. But this is the method by which you would derive that prediction, and saying if MLB was a ideal league where everyone had a 50-50 chance of winning any game, we would still expect to see winners and losers at the end of the season, and this would be the distribution. Now let's talk a little bit about this statistically a bit more. Hopefully this is a refresher for most of you. So you see here there is some dispersion. This is a Important word in statistics. There's some dispersion of this data, right? It's spread out. It's not all in one place. Now, for a binomial variable such as win, it's a 1, 0, it's binary. Probability of success we're assuming here is 0.5, or 50% of the time you're going to win. For such a variable, as we're illustrating here, the probability of success, or the proportion of successes over, well, here we'll say in games, is approximately normal. That distribution is normal. And so the winning percentage here, call it W percent, is approximately distributed normal with a mean of 0.5 or 1/2 and a standard deviation of 0.5 over square root n. Now in general, the standard deviation, which we will write as sigma, for such variable equals the probability of success, which here is 0.5, times the probability of failure, or 1 minus the probability of success, divided by n, and we take the square root of that whole thing, or we can say to the 1/2 power, however you want to say it. Now again here, since that probability is 1/2, the probability of failure is also 1/2, and so 1/2 times 1/2 is just 1/4. Gonna clear some room here. But then once we apply that 1/2 to 1/4, we get back 1/2 into the 1/2, or as I've written it up above, which means the same thing, 0.5 over square root n. And so the ideal league will have teams with equal probability of winning or losing any game. At the end of a season, we would expect the distribution of those winning percentages across team to be approximately normally distributed with an average of 1/2. So the average team should have a winning percentage of 1/2 and a standard deviation of 0.5 over square root n, where n is the number of games in the season. So what that means is if you have a season with few games like the NFL, you would expect the standard deviation to be very large, meaning the spread of winning percentages could be wide. You could have a lot of differences in winning percentages. Why? Because there's not a lot of games. So if you have, by chance, a lot more losses than average or a lot more wins than average, there's not a lot of time to make that up and get back to the mean. Whereas with baseball, there's 162 games. And so even if a team goes on a very rare winning streak or losing streak in this ideal league, there's many, many games to kind of average out that rare event. And so you would expect at the end of the season, all teams would be very close to 0.5. Whereas again, with the NFL, if any team goes on a losing or winning streak, there's not a lot of games to get back to where you perform on average. There's only 16 games, or there used to be. Now, since that winning percent is expected to be distributed normally, I'm going to go ahead and draw an ideal distribution again. The y variable here is frequency, and by that I mean the frequency of occurrences that we see a team with this winning percent, or the proportion of teams that fall under each category. Since this should be normally distributed, the winning percentages, in an ideal league, what that means is we expect exactly 68.2% of all teams in such a league to be within one standard deviation of the average, which is 0.5, or 50% wins. So we just talked about how that sigma, or that standard deviation, is a function of the number of games. So it depends on what league we're talking about. But once we calculate that sigma, 68.2% of all teams should be within one standard deviation of 0.5 if we're in an ideal league. We should have another 13.6% of teams on either side of that within another standard deviation. So to say that another way, within two standard deviations, we should have an additional 27.2% of teams. And then we should have a small number of teams, or fraction of teams, within 2 to 3 standard deviations. That should add an additional 2.1% of the teams on each side. So again, another way to say this, 68.2% of our teams should be between or within one standard deviation of the mean. We should have 95% within 2 standard deviations. And we should have 99, running out of room here, 0.7% of all teams within 3 standard deviations of 0.5. It should be a very, very, very rare event that we have a winning percentage of 100, and a very rare event that we have a winning percentage of 0. But again, how rare that is depends on the number of games. You imagine an extreme example where there's only 1 game in a season. Half the teams are going to have a winning percentage of 0, half are going to have a winning percentage of 1. If there's 2 games in a season, we might see some teams with 0 wins and some with 100% wins, but then we'll get some variation, some with 1 win. And as the number of games increases, as you can imagine, the likelihood of getting all wins or all losses goes really quickly to 0. It's the same thing as saying, what if I flip a coin? What's the probability I get all heads or all tails? Well, if you flip it once, the probability is pretty good. If you flip it 162 times, like MLB does, the probability is quite low. So this is really easy to calculate for the leagues once you know the number of games. For example, the NFL used to have 16 games per season. And so the standard deviation we would use to calculate what an ideal football league would look like is simply 0.5 divided by square root 16, which is, let's write it this way, 1/2 divided by 4, which is 1/8, or 0.125. So once we calculate this, we can go back to our normal distribution and plug in exactly the boundaries of +1, +2, or +3 standard deviations from the mean and see if our teams are fitting under the distribution as they should. Major League Soccer has a bit more games. Most of their season has 34 games. And so just to show you how this can change, the standard deviation there would be 1/2 divided by square root 34, which gives you about 0.086. So compare that to the 0.125 of the NFL. We would expect a lot less deviation from the mean for MLS. Now, of course, something that complicates this is that there are ties. So this is actually not an appropriate measure to use for soccer. Some have suggested ignoring ties or counting tie as half a win, and that's probably going to give you a decent approximation. Like I said, I did derive a better measure for games with 3 outcomes, which includes a tie, but did not publish it because after writing it, I noticed somebody else had the same idea approximately a year before me. Lastly, let's calculate the standard deviation for Major League Baseball, which has the most games in American sports. They actually have 162 games, so we're going to have a square root of 162 here, and that's going to give us about 0.039. So if baseball is a competitive league, ideally, we would expect very little deviation from 0.5. You should look at those teams' winning percentages, and they should be very, very, very tightly clustered around 0.5. Well, now obviously none of these are going to be perfectly ideal leagues. So a common thing we do is to calculate the ratio of the actual standard deviation that we see in the leagues divided by this ideal measure we just came up with. And we want to test whether or not that's close to 1. So this is our competitive balance measure, sometimes referred to as the Knoll-Scully, Scully measure, because these are 2 economists that came up with the idea to compare the actual standard deviation of winning percentages in a league to what would be ideal. That is, if every team had a 50% chance of winning every game. And so we can use statistical tests to see whether or not those 2 are equal, because the actual standard deviation will be approximated by the standard deviation of any given sample that we have from real-world data, and that is a statistic. So we can do a statistical test to see whether or not it is different statistically from this ideal measure, which will be a single number like we just derived. Now what we'll be doing with data, just to give you a little preview of this data assignment, is calculating the standard deviation from our sample. Now the standard deviation we just discussed was a theoretical one for the proportion of wins derived from a binomial variable, a 1-0 variable of whether or not a team won. So that was a theoretical derivation. When we go to get our sample standard deviation, remember the formula for that is to take the square root of the sum across all our observations, which here would be teams. So I'm going to write T for teams. We're going to look at the win percent, so I'm just going to write W, for team I, subtract it from the average, which should be 1/2, but for some it won't be if there's ties. Sometimes the NFL has ties. So for most leagues, this should be 1/2. We'll square those differences, add them all up across team, and divide by the number of teams. This is the standard deviation of a set of data. Now, what we'll actually do is divide by T minus 1. And when we do this, we call this the sample standard deviation, and we usually use lowercase s to represent it. Now, the reason why we do that is because this expression gives an unbiased estimate of what sigma really is. Sigma is the standard deviation assuming we have all data. So assuming we have every game ever that's going to be played and has been played of this league. We don't. You might think, well, of course we do. We have the data of every game that's been played. So in reality, yes. Empirically, yes. But we don't have every game that could be played. We only see the ones that have been played. So again, the theoretical standard deviation is giving us the spread of an infinite number of games. So whether or not we should use this sample standard deviation, which we will, is perhaps up for debate. Sigma gives us the standard deviation if we have the entire population of data. Now, if we're saying the only population we really care about is one particular season or a group of seasons, and that's the population, and we're not going to say anything about any game outside of that population, then perhaps we can calculate sigma. However, if you have a subset of data or a sample, then you're getting an estimate of the standard deviation. You're not getting the true standard deviation. That's why we use lowercase s. And it's been shown statistically, and you should have learned it in econometrics because it's a very straightforward proof, that if we divide by t minus 1 instead of t, this actually gives us an unbiased estimate of the true standard deviation. Now you can see when we divide by t minus 1, that's going to make the denominator a lower number, which makes our estimate greater. Now, an intuitive reason for why that happens with samples is because you are also calculating this average from the sample. It's a sample average. And so there's error there as well. However, here, I think maybe it's debatable because we know what that average is. It has to be mathematically 0.5. If there's no ties allowed in a league, that is 0.5. There's no error in measuring that. So I don't actually see this discussed much in the literature, but it's a point you could argue, I suppose. That is that we don't have to use the sample standard deviation. But in any case, it's not going to be terribly different regardless of what you do. Here we are going to use it until I could mathematically prove that it's unnecessary or not efficient. And I'm not there at the moment. Maybe I'll get there one day. So going forward, we will use this measure empirically of our data to get the sample standard deviation for whatever sample we're looking at. That will be our estimate of the actual standard deviation. And we will compare that to the ideal and see whether or not it's different than what we would calculate from the ideal distribution. Now, another thing I'll ask you to do, which is quite useful for visualizing what's going on, is to graph the ideal winning percent, depending on how many games your league has. I'm going to let you choose one of your own. I guess we can label this percentage of teams. I mean, frequency is appropriate, but let's be more specific. This is going to be the percentage of teams with each winning percent. And the ideal graph will look something like this. And then on top of that, I'll have you give me the actual distribution. Maybe, typically it doesn't look as good as it should. It usually has a similar shape, but no league is ideal. And so the green line will represent the actual distribution, and the blue line is ideal. And so it's really nice when conducting this kind of research to make figures such as this, to really visualize what's going on and how different things are. It's one thing to compare two numbers and say whether one's bigger or not. It's another to look at the entire distribution and you really get a better picture of what's going on. Now, if you're interested in this topic, there's a lot more with competitive balance. There's a lot more measures in addition to this one. But this is the first, this is the standard, and it's really simple to do research with. there's two paths you can take. Again, one, the uncertainty of outcome hypothesis. You can see if competitive balance changes across time for some league you're interested in, and see if that change in balance corresponds to changes in attendance or revenues. Do people care? Another path you could take is the analysis of competitive balance. You can look at time periods where leagues have changed the rules dramatically or changed the manner in which players might be traded or paid. Or look at a period of rapid expansion where you have a lot of new teams that you expect to not be as good as the more established teams and see if it significantly affected competitive balance. Did competitive balance as a measure itself change over time when these changes in policy occurred? These are all really fun, very simple research projects you could do. And every year I have a handful, and it's fine. So I hope that helps you understand what we're going to be doing here. I've listed another reference for you, which is a chapter from another sports economics book that talks about what we just went over. So if you would like another reference, more details, more examples, I would suggest you read that chapter. But now you're ready to understand what it is we're doing in this data exercise.